Can can
So
I
you can
start?
start, please. Yes.
Okay. Good afternoon, everyone. I hope I'm audible enough.
Yeah, why don't you start from the first slide?
This is you. We are from last week. You said we have to continue our presentation. This is not this
Oh,
week's.
okay. I thought it was today's presenter. Oh, all right. You can continue.
Okay, sir. So we are talking about conjugate gradient method, and this is a a popular method for solving large systems of linear equations, ax equals b. So it is an iterative method. We've discussed the direct methods like the Gaussian elimination. So this one is more of an iterative method where you keep on repeating steps until you have a convergence, something of that sort. So it's a powerful optimization method. So in mathematics, the conjugate gradient method is an algorithm for solving numerical solutions of particular system of linear equations whose matrix is symmetric and positive definite. So let's just go into the iteration steps. So this is like a sort of iteration steps to get what we want to do is we want to get a point at which our n converges as the number of iterations, our x, where it converges. So that's the end goal. Okay. So these are like the iteration steps. You can see we have like 6 steps. So these are the givens, or these are the things we need to take note of. So it says where x naught is equal to the initial guess. So your initial guess could be a column vector. We'll see that when I go to the next slide. Your initial guess is a column vector. Your A is your square matrix, n times n, or n by n. Then you have B, which is your given column vector. And then your R is your residual vector. We have the scalars, which are the alpha and the beta, and then we have our search direction. So these are all the things you need when solving this kind of linear equation. So this is the first step. We have our residual equals b minus a x naught. So I think we discussed this last week when we were talking about residuals. Okay, so this is like the relationship, or should I say the formula for getting this residual. And then these are the other steps. So let's go straight to what it looks like. So for example, you might be given a question like this. It says carry out 3 iterations of conjugate gradient method. So now we're using the conjugate gradient method for the following system of linear equations. So as you can see, we have something like ax equals to b. This is how all the equations usually look like, though you might have larger ones. So ax equals b. This is matrix A. As you can see, this is matrix A. This is the x. Sorry, there's supposed to be x2 here. This is x1, x2, x3 equals to this. So it could also look like this. So it could be given, you could see it this way, or you could see it this other way. So if you see it this way, you can convert it to looking this way, or to look like this. So you extract your 10, you extract your -6. Here you don't have x3, so that is 0. The next row is -6, 8. That way you extract it all, and then you have something like this. So recall ax equals b, where a is this, b is this. This is your column vector b, the given, or this is your given column vector v, or your known vector column vector b. Sorry. So the first step, if you look at that, if you follow this, the first step is d equals r naught. D equals r naught equals b minus ax naught. So this is first step. So the first step, or the first thing you should do, is assign x naught. You have to assign an initial value or an arbitrary value for x naught. That is, it could be anything, but we are going to have a column vector. This is a column vector. So you could decide to use 1, 1, 1. You could decide to use 1, 0, 0. But most people or most places, in most cases, you just use 0, 0, 0 to start. Okay, so your x naught, you just assign any column vector like this. So we have our x naught as this. Then going back to this, you can see you have this particular equation, r naught equals b minus ax naught. This is telling you that your residual vector is the same thing as this d naught, which is your search direction. So your r naught is equal to your d naught. It's the same value. So moving forward, we have r naught equals to b minus ax naught. So this is our b, 12, 0, 0. You can recall from the equation we are given, this is our b, then minus ax naught. Our a is this, our matrix, n by n matrix, and then this is our x naught, our initial guess, what we just started with. So you go ahead and do 12, just you are solving. So you do this multiplied by this. Once you multiply all this row times this column, this row times this column, this row times this column, you get 0 in the end. So when you subtract these two, you will get this. So your r naught is equals to this, 12, 0, 0. So remember, your r naught is the same thing as your d naught. Okay, so this is our initial search direction and our initial residual. So we've gotten that. Then the next step is this step 2, which is to get our scalar quantity. So we have this is our scalar, this is the relationship. Let me put it that way. This is relationship. So we have we have alpha. That's our initial alpha. That's what xi means. The initial equals to the residual transpose, then the initial residual over this. So we just follow the relationship. Then we are using initial, so we are using naught. We are starting with 0. So equals to, just replace the i's with the 0 because we are starting from that. Then remember that our r naught, we got this 12, 0, 0. Okay, so this is a column vector. But with this transpose means you just turn it upside down, you change it from a column to a row vector. So now it is a row vector because of this transpose. So it will look like this. Then your normal r, you put it, you just substitute everything basically. Here you have your d, which is the same thing as your r. Then you put it, then the transpose, then the matrix. Once you put everything and then you solve this. To solve this one, you do 12 times 12, that is 144. Then plus 0 times 0 plus 0 times 0, then you get 144. Then this, once you multiply this, you do 10 times 12 plus minus 6 times 0 plus this times this. The normal way you do matrix multiplication, you assume everyone knows how to do this. But if you don't know how to do this, I think it's really important to understand how matrix multiplication works. So once you multiply all these, you will get this. So your final answer for this initial scalar is 0.1. So move to step 3. Step 3 is now telling us to use this. So we have this, we are still working with the initial, which is 0. So you slot in 0 there, slot in 0, slot in 0. So in the end, you have x1, then x0 plus our scalar, and then our search direction, our initial search direction. So we have your x0, remember, is 0, 0, 0. That was your initial guess. You put it there, then plus this your x0, which is 0.1. Okay. Remember, we just got this one, then your initial set direction, put it, and then everything is straightforward. You multiply 0.1 times 12, then this time this, once you add everything, you get your x1. Then this step 4, you have this, we are still working with 0. Don't forget, we've not finished the first iteration. So we put in the 0 here, we have R1, put in the 0 here, then like that. We just substitute everything. are just substituting, and then you get your R1. So this step 5, we have this relationship. We are getting the second scalar. So we have two scalars there. We have the alpha and the beta scalar. So this is the relationship. And then same substitution, we're still working with 0. So you put in the 0s there, you have this relationship. So your R1, we already got our R1. If you go back, you see our R1, we got it as 0.720. just substitute here because of we have transpose, so it will change to a row vector. So like that, you get 0.6. You do this same thing, you keep going. So we are done with this is step 6. Once you do this step 6, the same, put 0, do everything, you get to this point. So we are done with all those steps. So at that point, we have to move to our next iteration where I equals to 1. We've used I as 0 and we've finished all the steps. You move to, so you can see here, what we got here is 4.3 to 7.20. So the next iteration is where I equals to 1. So you go back to step 2. You start from step 2. We are not starting from step 1, we are starting from step 2. So after the first iteration, you don't start from step 1, you start from step 2. So yeah, so we start from step 2. This is the same relationship. Now we are dealing with 1, not 0 again. So once you put it, you get your answer. You put 1, you replace 1 here, you get to this. So you keep on going. So after the second iteration, when we got to step 6, we got the 0.889, 1.491, and this. So the next iteration is where I equals to 2. So you just basically repeat the same thing. So we got to this point where we have our we have something like this, as you can see. So this is our x3. What you should be looking at is the value of x, because we are trying to get remember from the equation, we are trying to get this. This is what we are looking for, your x1, your x2, your x3. So we are looking for the iterations of the x. So this is our x3. So for the x3, we have what? 2.39, 1.99, 0.8. So looking at this R, the moment your R starts to converge, that's your residual vector. Once it starts converging, you can see this is 0.1, this is minus 5 times 10 raised to power minus 3. So when you convert it to be 0.000 like that. And so once you approximately, you can get 0, 0, 0. Okay, so it's telling you that at this point you can go ahead and stop, since you have a convergence here at 0, 0. So if you keep on iterating, you will see that you keep on getting these zeros. You can get 0 point something. So at this point, it's telling you to stop. So we are stopping at this iteration of x as x3. So this is where we are stopping. So this is our answer, or this should be the values of the x1, x2, x3, 2.39, 1.99, 0.8. So if you try using the normal Gaussian elimination to solve this particular problem, as we learned last time, you can see using that, you will get x1 as 2.4, you get your x2 as 2, and you get your x3 as 0.8 using the Gaussian elimination. Okay, and you can see 2.4 to 0.8. Let's look at our method when we use the iterative method. So we got 2.3, which is close to 2.4, right? For the Gaussian, here was 2, which is close, and here was 0.8 exactly. So you can see this is like the best solution, the closest using the iterative method for solving. So you could have this iterative method is very useful when you have a very large sort of matrix, or when you have sparse matrix. You can use the iterative method, and it's also get you your answer, or something very, very close to your answer. Remember, you can never get exact solutions. There are always some little negligible errors depending on. So that is how the conjugate gradient method works. So result x3 is a better approximation, like I told you. So than the x1, than the x2, x1, and x0. So if exact arithmetic were to be used in this example instead of the limited precision, then the exact solution would theoretically have been reached after n equals 3 iterations. That's after the third iteration, n being the order of systems. So I hope we understand that method. So we just need to know those steps. Once you understand those steps, it's just matrix multiplication and all. my colleague, I'll allow my colleague to continue from this point if we don't have any questions on that part. But if you have any questions, you can go ahead and ask me and I can give clarification.
Emmanuel, I have a question.
Okay.
You said that if you want to start the second iteration, now you have to start from step 2. Why?
Okay, let me. So looking at this second iteration, if we are to use our the step 1, which is, can you hear me?
I can hear you.
Okay, so if you have to use this second, if I had to use this one, which is R naught equals B minus AX naught. Let's go there. Sorry. So I'm trying to update. So we have let's see, we have Ri equals to B minus AX XI. So this is going to be this is Ri. So let's say this is going to be from, if I is 1, this will be R1 is equal to B minus A X X1. So looking at this, sorry, let me move this. So looking at this now, it's more like we are repeating. We've already gotten our R1 from this. Before we even got to this iteration, of I equals to 1, we had already gotten our R1. You can see here, we've already gotten the values of R1 in the first place. So doing this, it's going to be like going to the first step. I don't know if you understand me. If you can see here, we've already gotten the values of our R1, which is 0, 7, which is let me go back. So we've already gotten our R1 here. So using this will not, that's when I equals 1. This would be R1. So we've already gotten it. So there's no need going to this step again. So we'll always go through these other steps. I don't know if you understand. I don't know if you got that.
Yeah, I do. Thank you.
Yeah, so you just start from the second step and move forward, because you already have so that's it. Okay, so if there's no other question, I'll allow my colleague to continue from the next slide.
Okay, thanks, Mario. Please, can I share?
Yeah, let me.
Okay. Okay, can you see the slide show on my screen? Okay, can everybody hear me?
Yes, we can.
Yes, we can.
Okay, good afternoon. So I'll be talking about 3 topics: condition matrices, metric norms, and eigenvalues using the power method. Okay, I did a bit of condition matrices last week. So what's an condition system? So let's talk about when a condition is condition generally. So looking at this equation, x plus y equals 2 and x plus 1.001 equals 2. Now, the solution to this system of equation is that x equals 2 and y is equals to 0. If you solve it, okay, that's x is going to be 2 and y will be 0. Now let's assume that y imputing this equation in the calculator, for example, person makes a mistake and instead of x plus y 0.00y equals 2, it does 2.001. Now that's minute, 0.001. But when you now solve this equation, someone's mic is. So when you solve this, hello, Miriam or somebody.
It's not Miriam.
Oh, okay, sorry. Okay, so when you solve this equation, just because of an extra 0.001 mistake that was made in the results, right? The value of x is now 1 and the value of y is now 1 from x equals 2 and y equals 0. What changed? 0.01 was added to the output of the second equation. So this system is said to be an ill-conditioned system because a small change, a minute change in the coefficient, either the coefficient or the result, is causing a drastic effect. Okay, so it's said to be ill-conditioned. So this system that is what is called as an ill-conditioned system. So now let's bring it to a matrix. Okay, now when you say a system is ill-conditioned, it means that a small change will result into a large output. Small change in that coefficient or the result will result in a very big output. So now there's something called conditional number. Okay, in the field of numerical analysis, it is the number of a measure of how much the output value of a function can change for a very small change in input argument. So it is used to measure how sensitive a function is to changes or errors in inputs and how much error in the output results from an error in the input. We saw with that very simple simultaneous equation the other time. So now the most well-known example of a conditional number is conditional number of a non-singular square matrix. When you say a square matrix means n by n, 3 by 3, 2 by 2, 4 by 4. That's a square matrix. Okay. Now, and the formula for calculating the conditional number of a matrix is the norm of the matrix. So let's say you have a matrix A. So Ka, which is conditional number of A, is the norm of matrix A and the norm of the inverse of A. Okay, and the norm of the inverse of A. Now, when you say inverse, all right, when you say the inverse, sorry, I'm putting my note because I wrote some things down. Now, if a matrix does not have an inverse, all right, that matrix is said to be singular, right? If you can't get the inverse of a matrix, that matrix is said to be singular, right? But this is non-singular because that means you can't calculate the conditional number. Right, the conditional number will result to infinity. For you to be able to calculate the conditional number of a matrix, you must be able to find the inverse of that matrix. Now, so conditional number of matrix tells us how sensitive a multiplication. So when you multiply the norm of a matrix with the norm of the inverse, it gives us the conditional number, right? Now, the higher the conditional number, the higher the sensitivity of that matrix. How far the number is from 1. When the conditional number of a matrix is approximately or equals to 1, then that matrix is said to be well conditioned. But when a conditional number is significantly greater than 1, that matrix is said to be ill conditioned. If you have a matrix whose conditional number is 1, that matrix is well conditioned. If it is approximately 1, maybe 0.89 or 1 point something or 2, that matrix is still well conditioned. But when you begin to have conditional number like 10, 1,000, 4,000, that matrix is said to be very well ill conditioned. Okay, so when the conditional number matrix is close to 1, the matrix is said to be well conditioned. Now, matrix norms. Okay, matrix norms. Now, I hope you know how to. Now, before I talk about how to calculate conditional number of a matrix, I need to talk about the next of which is matrix norms. Like I said, the formula for calculating the conditional number of matrix is the norm of the matrix and the norm of the inverse. So we need to know how to calculate norm of a matrix before we now to get the condition number. Now, first of all, let me talk about inverse of a matrix. Everybody knows how to calculate the inverse of a matrix, right? It is 1 over the determinant of the matrix multiplied by, okay, fabricate. Let me not jump. I'm sure it should be in my norm somewhere. Okay, so matrix norm, what's the norm of a square matrix? Is a non-negative real number, right? Denoted by this symbol here. Okay, so now there are different ways of defining the matrix norms, which you are going to see, but all of them share the same property. That is, the norm of matrix must follow these 5 basic rules. Number 1, the norm of matrix must be greater or equal to 0. Like we said, the norm of a matrix is a non-negative real number, right? So it must be greater or equal to 0. Okay, if the norm of a matrix can only be 0 if the matrix itself is 0. All right, so if the matrix, if we have matrix A which is 0, then we have the norm to be 0. Okay, now if you multiply a matrix by a scalar number and you find the norm, it must be the same as when you get the absolute value of that same scalar and you multiply by the norm of the matrix. I'm talking about number 3. That is, if I pick a matrix A and I multiply by any scalar number, by any scalar quantity number, and I find the norm, whatever I get should be the same as when I use the absolute number, absolute value of that scalar K, and I multiply it with the norm of that same matrix. Number 4 is, if I add 2 matrices together and I find their norm, they must be less than or the same as when I find the norm of each matrix and I add them together. All right. So if I have matrix A and matrix B and add them together, then I find the norm. It must be less or the same as when I find the norm of matrix A and the norm of matrix B and I add them together. The fifth rule says that when I multiply 2 matrices, matrix A and matrix B together, if I find their product, right, and I find the norm, it must also be less or the same as when I find the norm of the individual matrix and find the product. So those 5 principles guide the normalization of any matrix. So we must not forget that the norm of a matrix is a real number. Okay, it's a number, it's a real number, which is the measure of the magnitude of that matrix. Now we have types of matrix norms. Okay, any questions? Someone let's say something. Hello. Okay. Silence means no question. Okay, so now the first type of matrix I want to talk about is the one norm. All right, which is the maximum absolute column sum. Simply, we sum the absolute values down each column, then we take the biggest answer. For example, look at this matrix I have here. Ignore my formatting, right? So we have a matrix 1 minus 7 minus 2 minus 3. This is a 2 by 2 matrix. Okay. Now, what we simply do is we sum the column, the absolute value of the columns down. That is, columns down mean we sum the absolute value of 1 and minus 2. So please, how can I like use a pen or something? Okay, I think I found it. So we
yeah, I think that matrix should be shifted in such a way that it's aligned.
Yes, let me see. Let me see, I can adjust that. Okay, so all right, so it means we add the absolute values of this guy together, which is what we do here. 1 plus the absolute value of 2 minus 2 will be 2. So 1 plus 2 give us 3, and then we do this together. So this is 7 plus 3. So we ignore the either positive or negative. So this is 10, right? So in this case, 10 is larger. So therefore, the norm of this matrix is 10. So this is one norm. Let's see another example. I think I have an example here. Okay. So look at this matrix again. This is one. Oh, I thought I had 2 examples. Yeah, sorry. So now this is another matrix. Let me adjust my slides. Sorry, a minute, please. Apologies for that. Okay. All right, so this is another example. This is a 3 by 3 matrix. You can still hear me, right? So in one norm, we sum these guys together, the absolute values of this, the absolute values of this, and the absolute values of this. So if we do 5 plus 1 plus 2, right, comma, this is 1. Then 4 plus 2 plus 1, this is another 1. And 2 plus 3 plus 0. We have 8, 7, and 5. The biggest is 8. So the norm of this matrix using the one norm method is 8. So we say the one norm of a square matrix is the maximum of the absolute column sums, right? That is the norm of a single, of a square matrix using the one norm, all right? Now let's look at another type of norm that we have, which is the infinity norm. The difference between one norm and infinity norm is one uses column, the other uses row. All right, one uses column, the other uses row. So in this case, in that other one, we sum down, column down. In this one, we are going to be using row. So what do I mean by row? In this case, we're also using the absolute value. So in this case, we're going to be summing instead of 1 and minus 2, we're going to be summing 1 and minus 7 instead. So we do this 1 and minus 7, which is 8, and minus 2 minus 3, which is 5. Don't forget we are using the absolute value. So absolute value of minus 2 will be 2, absolute value of minus 3 will be 3. So 1 plus 7 is 8, 2 plus 3 is 5. So the norm of this matrix using the infinity norm is 8. Looking at the 3 by 3 matrix, same thing, 5 minus 4 and 2, rather than 5 minus 1 and minus 2. If we do that, the norm of this matrix is 11. Okay, now let's go and compare the outputs. The first one, the norm was 10, whereas for the infinity method, the norm was 8. For this 3 by 3 matrix, the norm was 8, whereas for this, the norm was 11. Now it's 11. So let's go to the last one first, which is the Euclidean norm, right? Now in this one, it's more like you're using Pythagorean, right? The idea of very similar to a Pythagorean, where we square the root of the sum of all the squares. All right, so we find the squares of each of them and then we sum it together. So in this case, we have of each of the elements in the matrix and then we sum it together. So in this 2 by 2 matrix, we have 1 minus 7 minus 2 and minus 3. We find the square of each of them, we sum it together and then we get the square root. So 1 square minus 7 square, 2 square and 3 square sum together and their root is 7.937, which can be approximated as 8. If you use a 3 by 3 column, we get the same thing as 8. So the norm of using Euclidean is much more accurate and much more consistent than one norm and infinity norm. Because if you see, for a 1 by 1 matrix, it was 8. For a 3 by 3 matrix, it's also 8. Now, if you now look at the ones we have before, for a 3 by 3 matrix, we have 11. For the 3 by 3 matrix here, we have 8 here. And for one norm, we also have 8. So for 3 by 3 matrix, we got 8 here, we got 11 here, and we got 8 here. For a 2 by 2 matrix, we got 8 here. Sorry, for the one norm, we got 10. Infinity, we got 8. And Euclidean, we got 7.9. So they might not be the same, but it's around the same value, 10 and 8, 11. So now that we know how to calculate the matrix norm, right, we can go back to our condition number and calculate it. We said condition number is the norm of a matrix multiplied by the norm of the inverse of a matrix, right? And it is always bigger or equals to 1 most times, right? It is always bigger or equals to 1. Now, whenever we are you doing conditional number, like I said, we've seen 3 types of norm, matrix norm. But whenever we are doing conditional number, we must use the same norm twice. That is, you cannot use one norm to calculate this norm of A, then you're not going to use infinity norm to get the norm of the inverse. It doesn't work that way. It has to be the same norm. All right, because from what we can see disparity in the norms when we use the different methods. So whatever norm you are using must be used all through. You cannot swap norms in the same matrix condition. All right, so if you're using infinity, we use infinity or true. If you're using Euclidean, you use Euclidean or true. If you're using one norm, using one norm or true. Now, okay, before we do this, I said we have to get the inverse of a matrix. Okay, so now we want to calculate the conditional number of this matrix using the different norms we learned earlier, right? So this is 2 different matrices. This is A and B are the same matrix using one norm and Euclidean norm. We also now want to get conditional number for a 3x3 matrix. So we are going to use infinity norm for that one. Don't forget, the value for conditional number of any matrix is the norm of the matrix multiplied by the norm of the inverse of the matrix, right? So now for A, we want to use one norm, okay? To get one norm, who can tell me the norm of this? We are doing column down, right? Which is 2 plus 1. Okay, let me draw so you guys see what I'm highlighting. Okay, so with column down addition for one norm, right, using the absolute value. From this, you can see that the norm of this matrix is going to be 4.
4.
2 plus 1 is 3. 3 plus 1 is 4. So the norm is 4, right? Good. So now if we go here, so the norm is 4, which is what we have here. Now I want to find the inverse of a matrix. Inverse of a matrix is simply 1 over the determinant, and then we swap A and D. So let me say this is, so now this is A, this is B, this is C, and this is D. To get the inverse of this matrix, first of all, we get the determinant. Determinant is AD, that is, we cross multiply. A will multiply D, and B will multiply C. So this will be minus 1 multiplied by 2, which is minus 2, what we have here, and minus 1 multiplied by minus 3, that is 3. Remember, we are subtracting. So this is AD. This is AD. This is, pardon my writing. AD minus BC. Okay. So we said AD is minus 1 times 2, which is minus 2, which is what we have here, minus 1 times minus 3, 3. That is how we arrived at 1 all over. So we do 1 all over the determinant. So this is the determinant, right? AD minus BC is determinant of a 2x2 matrix, right? So we do 1 all over minus 2 minus 3. That's the first step. Let me use this. That's the first step, okay? Now, the next thing is we now swap, okay? We swap, this is the original matrix. Let me go. This is the original matrix. This is the original matrix, 2, 2, 1, 3 minus 1. Now we now swap. We swap 2 and minus 1. Okay, that's why we have minus 1 is now in position A, while 2 is now in position D. Then we now add negative to the value of C and B. So it was normally 2, 1, 2 and minus 1 for A and B. We swap. So it becomes minus 1 and 2. So 2 will be in D, minus 1 will be in A. Then we now add negative to the value of C and B. So it will now be minus 3 and minus 1. And that is what we have here. Please, is this clear? I guess so.
Can you go over it once again, please?
Oh God.
This
Okay.
inversion.
Okay, this is it. This is A, this is B, this is C, and this is D. All right. The inverse of a matrix is one, you find the determinant. How do you get the determinant of a 2x2 matrix? You cross multiply. So A multiplied by D minus B multiplied by, sorry, I made a mistake. This is B, this is C. Okay. So this is B and this is C. That was anyways. Main thing is you cross multiply, right? So minus 1 times 2 will be what? Minus 2. We write minus 2. Minus, always remember, it is AD minus BC. That's the determinant of a matrix. All right. So A times D minus C times D will give us minus 2 minus 3, which is minus 5. Minus 2 minus 3. That's what we have here. This is the determinant. We are looking for the inverse. So put 1 all over the determinant. Is this part clear? Yes, it is. So now, the next thing is we swap what is in A for what is in D. We now add negative in front of B and C. Okay. Remember in our initial matrix, this is the initial matrix, 2, 3, 1, and minus 1. So we swap 2 to where minus 1 is. We bring minus 1 to where 2 is. Then we now add negative in front of B and C. So that will be minus 3 here and 1 here. And that is how we arrived at this. Okay. So 1 over minus 2 minus 3 is 1 over minus 5. All right. So if you multiply what is outside with what is inside, 1 all over minus 5 multiplied by minus 1 will give you 1 all over 5. Same thing. So if you do the multiplication, you get this. All right. You get 1 over 5, 3 over 5, and all of this. All right. So now when you now do the norm, so we have our inverse now. This is A inverse. Okay. Let me draw. So this is A inverse. All right. This is A inverse. So if you now want to find the one norm of A inverse, remember we are doing column down submission, right? For one norm, we sum this and we sum this. Then the largest of them is what we now use as our one norm. All right. So 1 all over 5 plus 1 all over 5 and 3 all over 5 plus 2 all over 5. We look for the maximum, right? The maximum is 1. All right. So that is the norm of A inverse 1. So the formula again is conditional number is the norm of the matrix. What is the norm of the matrix? We did that up here, 4. And then multiply by the norm of the inverse. The inverse is 1. The norm of the inverse is 1. So that's 4 times 1, which is 4. This is the conditional number of this matrix using one norm. Do you understand? Good. Let's now do the same matrix using another type of norm, Euclidean norm. All right. Remember, Euclidean norm is the square of each element summed together, then find the square root. Okay. We've already gotten the inverse here. So we don't need to derive the inverse again. It's the same matrix we are using. This is the inverse. Okay. This is the inverse here. This is the inverse. So let's just use it down here. So now, first of all, we get the norm of the matrix itself using Euclidean. So the square of each element added together, then their square root. We get square root of 15, right? We're using A inverse from above, 1 over 5 squared plus 3 over 5 squared, we get 15 all over 25. So by the time we multiply 15 over 25 with square root of 15 over 25 square root, square root of 15 over 25 and square root of 15, the answer we get is 3. So using one norm, we get 4 for the conditional number. Using Euclidean norm, we get 3 for the conditional number. Quite close, but yeah, same idea. right? So this matrix is not well conditioned. Yes, the conditional number is not so big because the conditional number of a matrix can be 4,000. The conditional number is not so big, does not mean it is not ill conditioned, right? It's still bigger than 1, right? So it is not well conditioned, but it is not so much ill conditioned, right? So a matrix with a conditional number of 15 is more ill conditioned than this matrix. All right, now let's do for a 3 by 3 matrix using the infinity norm. Remember, in infinity norm, we are doing row instead, row sum. So we sum each of the rows, right, to get the norm, and the maximum of them is the norm. So by the time we sum each of these rows together, right, -1 minus over 3, the absolute value multiplied by 0 is 1 over 3. Same thing, 1 over 4, 1 over 2. All right, the highest of them is 1 over 2. Okay, so this is 1 over 2. Now, by the time you do the same thing for so now this is the norm of this, sorry. This is the inverse of this matrix. All right, we are doing the norm. Let me go back so that you don't confuse me. Remember, this is a 3 by 3. Okay, so this is the matrix. All right, we sum the rows -3, 4, and 2. All right, using infinity norm, what is the norm of this matrix? Very simple, it's 4, right? Because we are using absolute value. So 3 plus 0 plus 0 will give you 3. 4, same thing for 4, same for 2. Okay, so the norm of this 3 by 3 matrix is 4. All right, by the time you find the inverse using this method, by the time you find the inverse using this method, and you also find the norm of that using Euclidean, you get 1 over 2. By the time you multiply 1 over 2 by 4, the conditional number for this matrix is 2. All right.
Yeah, who is that one disturbing?
Okay, I've muted this. Why is Toby on me?
Who is that fellow?
Okay, all right. So now we are done with 2 topics I'm supposed to talk about, which is condition number, condition matrices, and matrix norm. The last topic I'm talking about is eigenvalue problem, power problem. Now, eigenvalue organization.
Yeah,
So
please,
now,
can you clean up all the illustration that you have there?
okay. So eigenvalue power problem. All right. So now, first of all, we need to learn how to calculate an eigenvalue. Then we'll now see how to use the power method to calculate it. All right. So truly, the thing is, getting the eigenvalue of a matrix can be done in different ways. Not much, but depends on, just like matrix norms and conditional numbers. So there is no one single approach to it. Okay. So first of all, before we know the power method, let's first know how to calculate the eigenvalue. Right now, want to calculate the eigenvalue. Now, there's no way you calculate the eigenvalue that you not get the eigenvector also. So, sorry, I'm trying to catch my breath. All right, so now to calculate the eigenvalue of an n by n matrix, first of all, we multiply the matrix by a scalar quantity. Then we subtract the identity matrix multiple. I will still explain this, right? Let me just list the methods. Then we subtract the identity matrix multiple from the matrix A. Then we find the determinant of the matrix and the difference. Then we solve for the values of lambda that satisfy the equation of determinant of A minus lambda I equals 0. So now we're just going to pick this. These are just steps. We're going to explain them one by one and follow it. Now, I have this 2 by 2 matrix, right? I want to solve for the eigenvalue of this 2 by 2 matrix using the step above. I had to do it on the paper and put it on my slide. So please, pardon my writing. All right, so step 1 says we multiply an n by n identity matrix by scalar I, right? This is an identity matrix. Okay, this is an identity matrix. So this is an identity matrix. 1 and 0 is 0 and 1. So we multiply it by a lambda. All right, then we have this. This is basically lambda times 1 is lambda, lambda by 0 is 0, lambda by. So we have this, right? Then step 2 now says we subtract the identity matrix multiple from the real matrix we want to get the eigenvalue. This is the real matrix. This is an example, 7, 3, 3 and minus 1, right? Now we want to subtract this from I. So this is A minus, so we're trying to arrive at the formula, right? We have lambda I, lambda times an identity matrix. Then we now want to subtract the matrix A from lambda I, which is lambda times an identity matrix. So let's say we have this matrix, we want to subtract it from this guy. All right. So by the time you do this, you have this. Okay, 7 minus lambda, 3 minus 0, 3, 3 minus 0, 3, minus 1 minus lambda, minus 1 minus lambda. Now, the next thing is we find the determinant. All right. By the time you find
please, can you run through that again with it?
Which ones are number 2 or number 3, sir?
From number 1.
Okay, so actually, okay, let me go back to the steps. So this is the formula actually. This here is the formula that we're trying to arrive, but want to follow a process. What we are doing is A minus lambda multiplied by, lambda can be any number, right? Lambda times an identity matrix. We find the determinant to be equals to 0. So that's what we are going through one by one. So I have my identity matrix, which is 7, 3, 3 and minus 1. It's a 2 by 2 matrix. Okay. Now, this is an identity matrix, 1, 0, 0 and 1. I multiply by lambda. I have this matrix, lambda 0, 0, lambda, right? Then I subtract it from my matrix, 7, 3, 3 minus 1. Then I have 7 minus lambda, 3, 3 minus 1 minus lambda. So now that I have this matrix, I want to find the determinant of this matrix. And we already know that determinant of a matrix is, let me clean this. So we know that the determinant of a matrix is A, this is A, B, C, and D. So determinant of matrix is cross multiply AD and BC. So if we do that, we have 7 minus lambda multiplied by 1 minus 1 minus lambda minus 3 and 3, which is 9. So we arrive at this equation, lambda square minus 6 lambda minus 16. Okay. By the time we solve that equation, we arrive at lambda equals to 8 and lambda equals to minus 2. So these are the eigenvalues of this matrix.
Please, can you clean all this your stuff? Getting okay.
So basically, the formula formula is determinant of A minus lambda I. All right. So you can pick out the formula and begin to evaluate it one by one. You can start with lambda I. So multiply lambda by any identity matrix 1, 0, 0, 1. Then subtract it from the matrix we have. We arrive at this matrix here. Right. Then once you are done, you can now find the determinant of that matrix. This gives you an equation that once you solve out, you get the value of lambda. So these are the eigenvalues for that matrix, 8 and 2. Okay. Now, we now want to look at what we call power method, right? Now, power method is particularly used for estimating numerically largest or smallest eigenvalue. Now, because like from what you can see, we can actually have more than one. In fact, for a 2 by 2 matrix, you have 3 eigenvalues. For a 3 by 3 matrix, you have 3 eigenvalues. For a 4 by 4 matrix, you have 4 eigenvalues. All right. So now that's a problem because for an n by n matrix, we are going to have n eigenvalues. So now the power method is now, so that's why you call it the eigen problem, right? So now the power method is now used for estimating numerically the largest or smallest eigenvalue and its corresponding eigenvector, right? Because we need to also know the eigenvector. So now, in the power method, it's actually iterative, right? So it can be used when the matrix A of order n has a linearly independent eigenvector. We'll still see that in our calculation. The eigenvalues can be ordered in magnitude. That is, if we have an eigenvector n by n, all right, we're going to have n eigenvalues, but we're going to have the biggest and the largest, all right? And it's not going to come. So power method is meant to help us to solve that problem of having a numerically large number of eigenvalues for a matrix, right? So now an eigenvector of a square matrix. So what's an eigenvector? An eigenvector of a square matrix A is a non-zero vector X, such that for some number lambda, we have the following. That is, we have the when you multiply the matrix and the vector, it's equals to the eigenvalue and the vector. If I have a matrix A and I have an eigenvalue, right? Now notice that I said for a 2 by 2 matrix, you have 2 eigenvalue. For a n by n matrix, you have n eigenvalue. Now, what is the how will I say it? What is the best eigenvalue in quotes for that matrix? It is the eigenvalue such that when you multiply, when you have the eigenvector and you multiply by that matrix, it must be equals to the eigenvalue and that vector. So the matrix A multiplied by the eigenvector must be equals to the eigenvalue multiplied by the eigenvector. That is how we know the real eigenvalue. Do you understand? So I have a matrix, like the matrix we were working with before, 7, 3, 3, and minus 1. Now we arrived at 2. Now, how do we know the best eigenvalue for this matrix? It is such that which of them that will I multiply by this matrix? If I multiply sorry, let me go back to my formula. If I have the eigenvector for this matrix, if I multiply the eigenvector by this matrix, it's the same as the eigenvector. So the eigenvector is for us to determine the best eigenvalue. That's what
Brahman, can you mute yourself, please?
So now, let's say we have this matrix 3 by 3 matrix. It says find the numerically larger eigenvalue of the matrix using the power method. All right. So this is the matrix we want to find. Now, the first thing is iterative. So let's pick a random value, right? We don't know what it could be, but we can test using any random value, right? Let's say we have 1, 1, 1. We can start with 1, 1, 1, 2, 2, 2, whatever. But let's start with a very small number, 1, 1, 1. Like I said, if I pick A and the vector, it must be equals to the eigenvalue and the vector. That's what we are trying to do. So AX, X being the eigenvector, must be equals to the eigenvalue multiplied by the eigenvector. That's what we're trying to do. So now we don't know what X is. So let's assume what X can be. So let's say we pick 1, 1, 1 as the eigenvector for this. So let's say X to be equals to 1, 1, 1, right? Now, if you multiply this matrix by this, right, we have 1 times 1 minus 3 times 1. We have 0, 7, and 14. I hope this calculation is clear. We multiply each of the elements by the individual row, right? So 1, 1, 1, right? So 1 times 1 minus 3 times 1, that's what we did. Now, when we sum it together, that's like using infinity method, right? Infinity method, we sum rows. Only that this one we are multiplying by X before we sum the rows, right? Now, when we summed it, we arrived at 0, 7, and 14. Okay. Now, what is the condition? What is the matrix norm for this matrix? Remember, it is the largest number. That is what? 14. Do we still understand that?
Yes.
Okay, good. So now, if the matrix norm is 14, right, and we divide everything by 14, we bring out 14 out of it. 0 divided by 14 is 0, 7 divided by 14 is 0.5, 14 divided by 14 is 1, right? Obviously, we say the largest eigenvalue is 14, and the
Hello, sir.
Sir.
Yeah, that's, you have 0, 7, 14 equals 14.
Yes, we are dividing by the maximum norm.
Now, that's where you got 0,
0.5 and 1.
Now, there's no division showing there. It's as if it's a multiplication.
No, we brought 14 out. Like if we multiply, yes, because that is what it is. If we multiply 14 by what we have our original matrix back, 0, 7, and 14. So it's literally like we brought out the largest eigenvalue out. So I don't know if you get what I mean.
No.
We are not
now,
dividing.
look at my argument. Now you have the iteration this up until you got where you have that circle 0, 7, and 14.
Yes, sir.
Then you brought out 14 as the highest.
Yes, 14, because if you look at matrix norm, sir, the initial topic we reviewed.
Yes,
we
I get that.
Yes, so 14 is the highest. Now, it's not like we are dividing by 14, actually.
Okay.
We are, I don't know the word to use. These are multiples of 14 or multiples of 7. But because this is the highest, we want to make them multiples of the highest, right? So if we bring out 14, if you divide all of them by 14.
Oh, factorization.
Right? Factorization, exactly, sir.
Okay,
if we factor by 14, we have 0, 0.5, and 1. If we put 14 back, we are back at this. That's just simply what we did. Because if we factorize by the highest eigenvalue, 14 becomes the eigenvalue, and this becomes the eigenvector. Because our formula says that the matrix multiplied by the eigenvector will be equals to the eigenvalue multiplied by the eigenvector. This is the
I don't know. Do you guys understand what he has just explained?
Yes, sir.
Yes.
All right.
So AX equals to lambda X. So if this is what we have, if we bring out 14, we can have our lambda and we can have our X. So from here, 14 is our lambda and X is our eigenvector. But
okay,
this does not
sorry,
mean...
sir.
Okay, sir.
For the sake of being explicit, now I feel that you should maybe move this one down. That's 14 when you are factorizing. So you put factorize this so that when those who are not in class are reading it, they will understand what you have actually done.
Okay, sir.
While getting your eigenvector.
Okay, so I will note that when I adjust it, sir. I will note that. All right, now, so I don't lose my thought process. So now this doesn't mean this is the, remember we are saying that power method helps us to find the largest and lowest, right? This doesn't mean that what we have is the largest, this is the best eigenvalue. Remember, a 3 by 3 matrix, we have 3 eigenvalues, right? So what we have here is just one eigenvalue. We need to see which is the, if we are going to get more eigenvalues, which is the largest which is the lowest. Now, this is the first iteration 1, x naught. Okay. Now we're not going to use what we got here as the eigenvector in the next iteration. Initially we started with a guessed number 1, 1, 1. All right. So now we have an eigenvector. Is what we're going to use in the next iteration, right? At the end of the first iteration, we had 14 and as our eigenvalue, and our eigenvector was 0, 0.5, and 1. Now that eigenvector, let's multiply it again with that matrix. Notice the formula we're working with is ax is equals to lambda x, right? So x multiplied by the eigenvector must always give us the matrix multiplied by the eigenvector. So if we multiply the eigenvector by that matrix again, same process, right? We have 0.5, 1, and 6.5. 6.5 is the largest value here. If we factorize by 6.5, okay, we have 0.0, 0.15, and 1, right? Let's use this same eigenvector again in another iteration, and we have this. Now, when do you stop? You stop when your eigenvalues are beginning to look similar. The previous eigenvalue was 14. Then we got 6.5. Now we are getting 5.92, which is almost 6. If we go again, what we are going to get is going to be something like 5.8, 5.7. So the moment you begin to see that, oh, your eigenvalues are beginning to look almost at the same number, because if you keep going, you get to a point where you keep getting the same eigenvalue. All right. So that means you have gotten to the lowest eigenvalue eigenvector. So we can simply say at this point that, so once you see that what you are getting is beginning to, the difference is not even up to 1, just about 0 point something, you can stop, right? You just stop. You don't keep doing the iteration again. So at this point, we can actually safely say that the largest eigenvalue for this matrix is 5.92304, and our eigenvector is 0.7692. Why did we stop here? Remember, we said ax must be equal to lambda x. It means that if I pick this eigenvector, the last one we are looking here, 0.07692, and I multiply it by my matrix, there will be hardly no difference. Do you understand? Because
quick question, sorry to cut you. You said the largest eigenvalue is the 5.92.
Oh, when we say largest,
numerically
largest.
Okay.
It doesn't mean numerically largest, because remember we are following the formula. What we are trying to get is a vector that when you multiply by the matrix A and you multiply by your eigenvalue, there is hardly no difference. All right. So if you pick this vector you are looking at here, this 0.076, 0.15, and 1, if you multiply it by your original matrix A, it's not going to really change the matrix A because it's small compared to when you have 1, 1, 1, which is the first one. Do you understand? Miriam, you asked the question.
Yeah. I mean, I understand that point. The point I raised was around calling it the largest eigenvalue. That's like my confusion, because I see like 14 is a larger number compared to 5.9.
Remember, it's the formula that we're working with. So ax must be equal to lambda x. It means x must be almost be a constant, something that doesn't change the value of both the matrix and the eigenvalue. So that is the power method. So you can calculate your eigenvalue, but if you have a 10 by 10 matrix, it means you have 10 eigenvalue. I need to know the best, which they call the largest. All right. And I know that my matrix multiplied by my eigenvector must be the same as my eigenvalue multiplied by my eigenvector. So it means that the lower the eigenvector. So if let's say your eigenvector is 1, for example, 1 times lambda will be lambda, and 1 times your matrix A will be your matrix A. Do you understand? So that's how we kept iterating till we got to a point where our eigenvalue was almost not changing for every iteration. So yeah, basically that is the eigen problem, value problem, and the power method for solving it. That is my presentation. So guys, going theorem, that should be Emmanuel. Thank you very much. Any questions? I guess I was quite fast at the end, but if no questions, then Thank you for coming to my TED Talk.
No questions.
Right, can we have Emmanuel?
Emmanuel, you can finish on Gregorian theorem.
Yeah,
Should I
start out
start?
with the class.
Okay.
Okay. Okay, so the last subtopic here is the Gregorian theorem. Okay, the Gregorian theorem, or you can also call it, you might see it in some places as the Gregorian circle theorem or the Gregorian disk theorem. So you can see it any way. So it says it helps, so the main aim is to help figure out what range the eigenvalues of a certain matrix would be. Okay, so it's giving you the range, it's not giving you the exact. With this theorem, it's a theorem, it's not for solving a problem. So it gives you a range of, okay, your eigenvalues could be between this number and this number. And so that's what it's, let me just go ahead and explain the theorem. So looking at this, it's saying like this is D. This is representing the Gregorian disk. Okay, so there you have D1, D2, as many as, depending on how large your matrix is. If your matrix is n by n, it could be 5 by 5, 6 by 6, but this disk goes like D1, D2, like that. Okay, so it's saying that, for example, let's say I is 1, so D1 is the set of points in a complex plane, such that the absolute value for the magnitude z is less than or equal to the sum of the absolute values of the other entries in the first row. Okay, so this is the radius. This is r signifying the radius, okay, which you will get. So this is matrix. This is matrix A. Okay, so there are lots of diagrams here. So I think from the diagrams we'll better understand the theorem. So this is what our R this is what our R signifies. So it's saying that the sum of the absolute values of the entries of the first row. Okay, let's use okay. So we have something like this now. We have a matrix, and so it's saying the sum of the entries of the first row. So for example, we are going to get our radius, which is our R, which we are looking for. We are going to let me annotate. So let's assume this is our diagonal. This is our diagonal. Sorry. Okay. So this is our diagonal 4, -5, and 3. So to get your radius for the first one, which is our C1, we will have 2 plus 3, the absolute values of 2 and 3. So remember we saw something like this. Need to go back. Sorry, can we see my screen? I'm trying to move back. I don't know if it has. Oh, okay. So we have something like this, where this is our radius. So we have the summation of the entries of the first row. So this is M, that is Ij. So I could be 1, J could be 2. Note that I and J cannot be equal. So this could be for this matrix, this is your A11, right? This is A12. So it's telling you that that this value cannot be A11. Okay, so we are excluding this. We can't use this. So it means your values can be this. That is A12, A13. So this is A21, A22. So it's telling your values, your radius cannot be this, and this is A22, A23. So this is our diagonal. So to get the radius, we're adding, for this first row, we're adding 2 plus 1. That's the absolute values of this. 2 plus 3, that is 5. Then for this one, we are adding the absolute values of -2 and 8. That is going to give us 10. Then for this last one, remember we are excluding this diagonal. So for this one, the radius is going to be the absolute value of 1 and 0, which is 1. So this Gershgorian disk is, let's assume we have something like this, which could represent a plane. So let's assume we have something like this, which could represent a plane. So we have we've gotten our radius from this matrix at 5, 10, and 1. So 1 is going to be somewhere close to, on the x-axis. 1 is going to be somewhere close to this point. Let's assume this is 0, this is 1. We could have our 5 here in this point, and then our 10 could extend. Okay, this is showing as 10. So we could have our 10 here, we could have our 5 here, we could have our 1 close to this point. So we just pick these are positive numbers. Okay, if you have something like -5, you know it's going to be at this other side of the plane of the graph. So, but we have 5, 10, 1. So we have 1, 5, 10. This is not accurate, but it's just a representation. So to draw these circles, or how these circles are gotten, is after getting those points, which is your radius, you will now have you are looking at these diagonals. Okay, so these diagonals are what you would. These points, and it's not this. I mixed them up. We are dealing with this. These are the values we are dealing with. The diagonals is what you draw here. So we have 4. 4 is going to be around here. 5 -5 is going to be at this other side. Okay, while 3 is going to be at the positive side of the x-axis. So your radius is going to be the radius of the circle itself. So for 4, which is the first one, 4 is around here. Remember it's the center point of this C1. So the radius is going to be 5. So that's how large your circle will be. That's the radius of that circle. So let's assume the circle is let's say we are looking at this circle now. The radius is going to be from the center to the other end. That's 5. You draw the circle. Then for -5, we'll have our radius as 10. The circle is going to be a whole lot bigger than the other ones. And then for this 3, we have the radius as 1, which is the smallest circle. So this is just telling us that it's the union of these disks is going to lie in D1 union D2 union D3. Okay, I don't know if you understand what I'm trying to explain from this. It's telling us that the eigenvalues is going to lie in one of these disks. So there's the possibility you have your eigenvalues in just one disk, like one disk like this. You could have your eigenvalues. There's a possibility that you could have more than one eigenvalue. You could have 1, you could have 2, you could have 2. So there's a possibility that your 2 eigenvalues could be in just one disk also, or 3 of them, 3 eigenvalues could be in 3 disks. So there are sometimes you have unions, there are sometimes you don't have unions at all, where this circle don't even meet each other. They could be far off each other in the plane. Here you can see some intersections or some unions, but there are some times where these circles don't touch each other. And in those individual circles, you could have the eigenvalues inside those circles. Sorry, I'm trying to. I don't know, my screen is now. Okay, so this is another example. It says the Gershgorian theorem of y-axis is interpreted as the imaginary axis, since the root of the characteristics polynomial could be complex numbers. They take on the form x plus iy, where I is the square root of -1. So it's also telling that there's a possibility that this could be complex numbers, where you have you could have 1 plus I, you could have -5 plus I. These are complex numbers already, and also you might not have it this way. So in whatever case, you do the same thing and you get the radius. Okay, for this one, we take the diagonal as this, and then you get your radius as the absolute of this plus this, you get 7. The absolute of 2 and 0, you get 2. The absolute of 4 and 4, you get 8. So you just draw out the circles, you draw out the circles. So you can say that we see all the eigenvalues lie in the union of all the circles. Okay. So because this one, the circles, after drawing them, the circles are meeting each other. So there's a union. If they're not meeting each other, then there's no union between those circles. And so there are other should I say, methods that can help you solve. This is just a theorem telling you, just trying to show you that yes, there's an eigenvalue in this particular matrix, or in this particular matrix. So you have other methods that can now help you to solve, like the power method that my colleague just explained, that you can use to get the actual eigenvalue of a matrix. So this is just showing that yes, this particular matrix actually has eigenvalues. So these are other references, at least from what I could understand. This is just a theorem. There's no solving for anything. So these are links to materials you could use to better understand the theorem. So I guess that's the end of our presentation.
All right. Thank you for your presentation. Well, I felt the lecture was quite explanatory, so you took a lot of our time. But of course, it's worth the time taking. But I don't know if there are questions or concerns about what has been taught by the individuals. Yeah, do we have questions? All right. In the absence of no question, I think, what time is it? This is 2:30. Now we have just 30 minutes. Okay. Who are the presenters for the session 4? Can you raise up your hand, please? None of them is around. Section 4. Who is Bankole? Okay. Who again?
Lawa Farouk, sir.
What?
Lawa Farouk.
What is it? Yeah, I'll raise up your hand so that I can make you co-host. I can't see any hand raised. Okay, I think I've seen one hand. There's one Cindy. This is a leg lady clapping. What's it mean? Okay, Cindy. Okay. Again. I think I'm not seeing any other person, just one individual. All right. Are you Cindy Sontian or something? Soton? Okay. Are you the one presenting for your group?
Yeah, Bankole too is there. Cindy Bankole.
Yeah, I'm one of the people presenting for the group, but not.
Who is the opening presenter?
Lawa is sharing his page, this thing for us. It's screen for us.
Who is Lawa?
Hi, sir.
I can't see any Lawa. Yeah, just raise up your hand so it'll be easy for me to find. Oh, Farouk.
Yes, sir.
Okay, just keep moving up and down more. Yes. So you can share your screen now. Let's just have the introductory remarks. Yeah, can you put it in slideshow, please? Let's press F5.
Good afternoon. Bankole, you can start.
Put it on slideshow, please.
It's on slideshow already.
No, it's not. Am I seeing another thing? The screen has disappeared, I think.
Can you see my screen now?
Yes.
Okay.
So you have 10 minutes.
Bankole, you can start.
Good day, everybody. My name is Bankole, and I'm here to present on nonlinear equation. A simple nonlinear equation is of the form ax squared plus by squared equals c. A nonlinear equation looks like a curve when graphed. The degree of nonlinear equations is at least 2 or other higher integral values. With the increase in the degree of the equation, the curvatures of the graph increases. The input and output of a nonlinear system is not directly related. We have various types of methods of solving a nonlinear equation, but this course, we will be looking at the 4 major types of solving a nonlinear equation, which are bisection method, fixed point iteration method, secant method, and Newton method. Please move to the next slide.
On the next slide.
So one of the first numerical methods developed to find the root of a nonlinear equation, function x equals 0, was the bisection method, also called binary search method. The method is based on the following theorem. Theorem 1, an equation, function x equals 0, where function x is a real continuous function, has at least one root between a and b. If function a, function b is less than 0. Note, if function a, function b is greater than 0, there may or may not be any root between a and b. If function a, function b is less than o, then there may be more than one root between a and b. So the theorem only guarantees one root between a and b. Since this method is based on finding roots between 2 points, the method falls under the category of bracketing methods. Next slide, please. Identifying a bracket including a root with points a and b such that a is less than b and function a, function b is greater than o.
Yeah, well, I think I find your presentation as if you are reading. And when you say function A, function B, less than O, that's not O, that's 0. Then function A multiplied by function B. You should speak like a mathematician, not like...
I'm sorry, sir, about that. Determine the midpoint of A and B. Let's say C. That is, C equals to, open parenthesis, A plus B, close parenthesis, over 2. Let's check C. If function A, function C is less than 0, then A remains, but B becomes C. And if function A, function C is greater than 0, then A becomes C and B remains. If function A, function B equals 0, then C is a root. Repeat the procedure until desired accuracy is achieved. Stop iteration when B minus A is greater than 0. Is less than 0. I would like to hand over to Lawal now, my colleague Lawal, to continue from the examples.
Okay, thank you very much, Bankole. So now, we are given an example here that we should find the root of the equation s raised to the power 4 minus x minus 10 is equal to 0. So here we are given the number of iteration we are to use using bisection method. So here we are given 2 points already. We are given point A to be 1.5, while point B to be 2. So now from the algorithm, let me go back. The algorithm, it gives the first step is identify two brackets. Identify a bracket including a root with the point A and B. So such that A is less than B, and if function A multiplied by function B, it should be less than 0. Yeah, from here now, if anything will be less than 0, we should know automatically that that value should be minus. It is only a negative value that can be less than 0. So here now, the first step to just check, maybe the function of A and the function of B that they give us will give us a negative value. So here we input A into the equation, s raised to the power 4 minus x minus 10. When we input the value of A into the equation, we have negative 6.4375. And while B is 2, we input B 2 into the equation, we have 4. So if we multiply this function A and B, we know that we have a negative value that is minus 24 point something. So the first step is correct. So now, since we have two different signs, then we can proceed with the iteration. So the second step here is we are going to find the midpoint between the two points. So if you are finding the midpoint into the 2 points, we are given the formula that A plus B all over 2. So we have 1.5 plus 2 all over 2. That one will give us 1.75. So I just want to bring it into this table. That is the first row. We see first iteration. We are given the value of A to be 1.5, the value of B to be 2, while the function we got for A is minus 6.437, and the function of B.
Sorry, Lawal. Sorry to cut you short. I was just wanted to ask, how did you get the power of 4 to calculate the function of A?
No, it is given from the question. The question is 4 is x raised to the power 4 minus x minus 10 equals to 0.
Okay, so you pick the highest power when calculating for
the
function.
No, I input the value of A to be x in the equation.
Okay.
Yes. So can I go on?
Yes, please.
Okay, thank you. So the function of B is 4. Why this place is C? There's a mistake here. This place is C. So our C is A plus B all over 2. So our midpoint is 1.75. So now we are going to find the function of C. If we put the value of C into the function x raised to the power 4 minus x minus 10, we are going to get minus 2.3711. We can see here that the function is not close to 0 because we can only stop the iteration when the functions are close to 0, like 0.00 something. So now we go again. Now let me go back. From here, check C. We are given 3 conditions here that if function A multiplied by function C is less than 0, that is the function of C that we got. If we multiply it by A and it is less than 0, that means we know our function A is negative, and our new function C now is negative also. That means if we multiply it, it's going to give us a positive value. So A will remain, but B becomes C. And the second condition, if we multiply the function of A and the function of C, That is, function of A is negative and function of C that we got is negative also. That will give us a positive value. So we cannot get a root for a negative for a positive value. We cannot get a root. Why the function of C? Why the third point is if the function of A and the function of B is equals to 0, so that's our root. So I'll come back here. So since our function of C is a negative value, then we just we take our C now to be our new A. We take our C to be our new A, which is negative. One of the roots must be negative. Our C now is our A, which is 1.75. So our B remains, which is a positive value, to be 2.
Mr. Farouk.
Yes, sir.
Well, thank you for your presentation so far. I would like to crave your indulgence that maybe we start from the example in the next class.
Okay.
Now, the reason being that after now, I have another class.
Okay.
So, and I have to quickly run through the attendance and also grade those guys that presented last week.
Okay, sir.
So we start from this slide in the next class, right?
Yes, sir.
Yeah,
Thank
so
you.
the first, okay, let me quickly run through the attendance. Who is this fellow? All right. Who is Odedi Moses?
Odedi Moses, present.
Oh, sorry. Akinrola Bu.
Present, sir. Akinrola Bu, present, sir.
Emmanuel Kwechuku, that first name.
Present, sir.
Ezekiel Tobi. 0. Elegbedi Bankole.
Present, sir.
That voice seems it has not slept today. Samuel Chika.
Present, sir.
Abdul Rahim Miriam Bukola.
Present, sir.
Okay. Agba James.
Present, sir.
Namdi Chukwemeka.
Present, sir.
Usagilduwa. Ebenezer.
Present, sir.
Shontan Cindy.
Present, sir.
Akinwande Akinwande. Okay, sense. Oluwasusi Victor. Oluwasusi Victor. Okay, thanks. Lawal Farouk, present.
Present.
Oladipupo. Olu something. Is it present? Okay. Muslihuddin.
Present, sir.
Okay.
Present, sir.
Abdul Salam Miriam.
Present, sir.
Fakorede Olumide.
Present, sir.
Ogbaji Michael. Ogbaji Michael. Okay.
Present, sir. I was trying to unmute. Present.
Uluka Prince. Okay, has he withdrawn? Jebutu. I can't hear you, but I think you're trying to talk. Moshood Aliu.
Present, sir. Morifelu Ajebutu.
Yes, I've seen that. Moshood Aliu. He's present. Okay, he's absent. All right. So who are those that presented today?
Morifolu Ajebutu, sir, and Emmanuel.
What? Okay,
Jebutu.
Okay, Jebutu, and who?
Emmanuel Mbemena.
I presented last week, sir.
I know.
Okay, sir.
What's your surname?
Musliuddin Abdulrahman. Musliuddin.
Okay. Then the other person?
Mbemena Emmanuel. Mbemena is my surname.
Your presentation was very bad last week, but it appears there's an improvement today. So I'm going to upgrade you. So get you +1. Yeah, so, and I think you make corrections to your slide and let us have it on the chat group. Is that okay?
Yes, sir.
Yeah, so we'll grade you on your slides when we get it. All right, so thank you for your time. The next set, that's Mr. Lawa's set, we'll have our presentation next week. So chapter 5 will be upper week, right? All right, so have a pleasant weekend.
Sir, please, as Jebutu Morifolu have been graded, sir.
What?
You didn't ask for my son, sir.
Jebutu. How many of you presented? Just 2 now?
Today.
Last week?
Last week, just 1 person now. I didn't finish.
Who is that fellow?
So last week. I
Sir,
was the first
man presented last week. Then I continued.
So last week, Musliuddin Abdulrahman. The second was Emmanuel, and the third was Jebutu, but it was just for a very short while.
Yes, I've seen Jebutu. I've seen Emmanuel Kichuku. Who is the last person?
Musliuddin Abdulrahman. I presented last week. The first presenter last week.
Oh yes, yes. I've seen your name. All right. I've graded it as last week.
Okay, sir.
All right. Thank you. All right. So please have a pleasant weekend. Let me run into the other class. Hello. Yeah, you can check the YouTube channel, or at least for a recap. Let me see if I can copy the link. Where's the chat? Oh, I think some people were even trying to chat. Oladipo. Owode is present. I didn't get that. Let me quickly look at it if I have not closed the attendance. Oh boy. I'll close the attendance. Coming low. The issues. You should have spoken before closing all this up. So that's the YouTube channel. So, sir, will you be at the office on Monday? Who is this lady? No, I will not. So I'll take note of. All right, so pleasant day. But you could call me. That's the Ladi. Is it Ladi? Yeah, Ladi.